Well, hello everyone. Thank you for joining us today for this webinar. My name is Masha Petrova. I'm the CEO and co-founder of Nullspace, and I'm excited to present this webinar to you today. With me, I have Katerina and Henrik, who will take over the technical part here in a second. But for those of you who are new to Nullspace, we'll start by introducing what Nullspace is, just for a few minutes, and then I'll hand it over to the technical team. So, what is Nullspace? Thanks, Henrik. Go ahead to the next one. So Nullspace is we develop simulation tools for electrical engineers. Specifically, Nullspace AM and Nullspace Prep are our tool suite for a full wave 3D electromagnetic simulation. So Nullspace AM is a full wave 3D electromagnetic solver. And for some of you that we see some familiar faces here or familiar names, you might know that we compete directly with Nullspace, with ANSYS HFSS, and so CST tools, for example, which are also full wave simulation tools for simulation of electromagnetics. So the difference between Nullspace and the legacy tools is that we are a modern implementation, or Nullspace is a modern implementation of frequency domain method of moments solver, which makes us very fast without losing any accuracy in the simulation results. We feature a proprietary large-scale matrix compression algorithm in our solver, which compresses the matrix on the fly and makes the simulations, again, faster without losing any accuracy. We also have features like high-order basis functions, high-order geometry representation, in our solver, which makes our results very accurate. Again, fast direct solver technology. We also have multi-CPU and multi-GPU acceleration. So the Nullspace simulations run faster whether you have just the CPUs available to you or if you have GPUs on your machines. Nullspace can take advantage of that for even faster simulations. And also we have a very powerful, flexible Python API for customization and integration that underlies the whole Nullspace simulation, which makes it really easy to drive with AI tools, for example, and to set up complex optimizations. Go ahead next, Henrik. So the question is, why another simulation tool? Those of you familiar with the space who have been simulating things for a while know there's not many tools available out there for engineers on specifically full fidelity simulation side of things, right? In fact, the legacy tools, commercial tools that many of you probably use are relatively old. So these are tools that are, 30 to 40 years old as far as the solver is concerned. They're not designed to scale. They're not designed for modern parallel computing architecture. They're not designed for the age of AI. And so they struggle when it comes to electrically large problems, like the one we're going to show today in this webinar. And so if you need to simulate an antenna on a platform, for example, as opposed to an antenna in isolation, it could take a very long time for a single simulation to run. And there is lack of optimization, uncertainty analysis options, or you can do it, but it's not ideal with the legacy tools. And, obviously many of you are probably familiar with very expensive, very cumbersome licensing for the commercial legacy tools that are available today. So that's all the issues that Nullspace has set out to address. And with that, go ahead to the next slide. I will hand this over to our technical team. We're going to talk about a very exciting application, an automotive application today of an antenna on the body. So Katerina and Henrik, I'll hand it off to you.
Thank you, Masha. Hello, everybody. My name is Katerina Galitskaya. I am senior antenna engineer with more than 10 years experience in various types of antenna design, customer electronics antenna, base station antennas, millimeter waves, IoT, all kind of antenna design. And some of you might know me from my LinkedIn post. I'm very passionate about simulation, really passionate about like antenna design, kind of debugging some myth or some mistakes in antenna design. And I relatively new to trying this tool, Nullspace, and I'm really interested in seeing its capabilities. And yeah, I'm really excited to show you this simulation that we've done with Henrik.
Yeah, hey everybody, my name is Henrik. I'm the lead application engineer here at Nullspace. I have been working in different antenna companies with antenna designs the last 18 years, both on the commercial side and the defense side. And I started out doing that in Sweden, but since 14 years back, I'm located here in the US. So I'm excited to also ask Katarina, and I'm excited here to be on the side by side here with Katarina to show you what we have done. So let's get into it.
Yeah, let's get in. And please, if you have something to ask, just put it in a chat or Q&A while we go, and then we will address. We will have like 10-15 minutes in the end, and we will have this interactive conversation with all the questions. So why do we need to simulate automotive antennas now? Especially now, it's very important because we have our systems that most of you know, like maybe own a car, that we have a lot of systems inside, a lot of wireless radios, right? We have cellular, we have Wi-Fi, we have Bluetooth, maybe we have some like a driver assistant systems there. So it's all a lot, and it's all in the environment of the car, right? So we have now we're moving from 4G to 5G. We have more bands. So if before, like some years ago, we had only like 700 megahertz band, now we have also higher bands like 360 and even higher with 5G, right? Then we have our Wi-Fi that's also now dual band, right? We have 2.4, we have 5 gigahertz. And so it's all in the environment of the car, and it's all coupling together. We have a lot of this system that shouldn't be like communicating a lot, right? They should be decoupled. They should have good isolation. And just by simulating one antenna in a free space, then another antenna in another like open model, right? That will not give you results. All antennas should be in the environment, in the final environment, right? So if it's installed on the car, then we simulate it on the car. And on the next slide, you will see that this is actually not as trivial as it might sound, just to put your antenna on the car, because if we talk about 1 gigahertz or 3 gigahertz, which like we have now in our cellular systems, right, bands, 700 megahertz, 900 megahertz, and then 3000 megahertz as well. That's all. If you think about wavelength, that's just a fraction of meters. But the car is several meters long, right? It's like 4 meters long. Like in America, maybe some people say even longer, so bigger, right? So we have this small antenna with a very small wavelength that we want to mesh correctly, that we want to have like all our currents, everything calculated correctly, right? With the full wave solver, ideally. And then we have this gigantic car, right? That if we mesh the same, if we simulate it like just kind of like straightforward, that will take forever, and that might not even work at all. So that's why a lot of tools that we kind of familiar with, usually the approach for that is to kind of have several models. Model for antenna when we have full wave simulation, and then we have car, and maybe we combine them, and then we run everything with the asymptotic solver with maybe shooting bounds and rays, and that's how we get results. Some results maybe like somehow accurate, but like with the assumptions of these solvers, right? With all the limitation of these solvers. That's why it was very interesting for me to have this, like to simulate the whole system. What you see here, this big car with two antennas that we designed with Henrik, and run it with the full wave solver. So Henrik, what do you think? What is the advantage of running it with the full wave solver?
Yeah, so when you finally put your antenna on the car, you want it to work, and why should you do assumptions?
Yeah.
So up to now, yeah, you could use these asymptotic solvers where you still simulate the whole car, but you don't want those last-minute surprises. You want to know exactly what you're gonna expect when you go to production. So that's what you're gonna get with using a full wave solver.
Exactly. So We can now move forward and see like exactly the simulation. So what we did with Henrik is we run our antenna, PIFA antenna, MIMO with the two ports. We run it in the free space, like what we would usually do, right? We run antenna in the free space, and then some people just hope for the best and see that okay, that will work. But then we kind of moved a second step. Next step, we integrate the antenna on the vehicle, and also very interesting for me was what we've done is that we simulated several cases. So one with the like normal vehicle with the metal roof, and then with some fancy car with the glass roof, right? So some modern fancy car, because like you might think like what is the difference, right? It's still this huge car. What is the difference? But we will show that there is difference with this configuration. And then we also simulated some multiple system in the car. So we put like Bluetooth, Wi-Fi antenna inside the car and like checked if there is any good isolation between the antennas. So we start with the free space simulation with the standalone antenna, and our antenna is relatively simple for this presentation, right? Modern systems, they have these shark fin antennas on the top. Like this is exactly what we did, the simulated shark fin antenna, but it has a lot, maybe more things inside, right? It has a lot of more bands inside, maybe some different radios as well. But we just kind of stopped here. We designed this dual band antenna, MIMO support with the two ports, and then we had the glass fiber radar on it. And then we did the meshing, and Henrik will talk more about the meshing.
Yes, so here I wanna highlight something that is done a little bit different in Nullspace, but it's a really good thing here, and that is that if you look at the slots here of the PIFA antenna, you can see that the mesh is a little bit denser, and that is what you would expect from a antenna, because you're gonna have a little more concentrated currents around the slots. All these mesh lines that you see here has actually been controlled by the user of the program, so that you are setting these different let's say mesh intervals, for example, here on the slots, to drive a tighter mesh directly from the beginning of the problem. So compared to, for example, an adaptive process that is used in CSD HFSS, where you just hit play, it goes through these different iterations where it improves the mesh, and hopefully before you are out of your adaptive max passes, you will have a good enough mesh that will actually be an accurate result. But here in Nullspace, we are skipping those steps by controlling the mesh by ourselves from the beginning. And that means we just set it up and run a good mesh from the beginning. And sometimes, or many times, when you have these special cases in, for example, CSD HFSS, you end up in the end of the day anyway to go in and set a special mesh setting in the slots here, for example. So we are just want to point that out, that we go straight to the right solution here by controlling the mesh from the beginning.
Yeah, exactly. And I want to add that even with this adaptive meshing, right, that what we have sometimes in some tools, we still, like, for example, I myself, if I work with some other tools, I still do some manual meshing. Like I need to this control like myself because the adaptive mesh, yeah, it's good, but I still need to have this control that really, like, especially in these kind of tricky parts, right? Like where a lot of happening, a lot of currents. I really want to be sure that mesh is correct. And if we move forward for the next slide for the
Yeah,
results.
I just want to mention one more thing. For example, when you run the adaptive meshing and you add a little detail, next time you run the adaptive meshing, it might be different again. But if you here in
Right, right.
Nullspace, when you set the intervals, you're always gonna get the same mesh from
Yeah,
your current
true.
project.
Yeah,
So,
yeah. So it kind of adds to repeatability of the design, and that, or
right.
between runs as well, you have this like that you can predict what's happening. So This is the results of our standalone antenna, and a lot of people just stops here, right? They have antenna. We have some dual band resonance happening, so we have on 700 megahertz approximately, then like 300, 3,700 or 600. That's what we were aiming for. And then we have like this is like 3D radiation pattern that many of you can recognize. It's nice. It looks as you expect. And you might think, okay, like now I've done right. I kind of I finished my design of antenna. I can put it on the car or wherever. I can put it wherever, and it will be the same. So here we have some spoiler alert that it will not be the same. Yeah. You can move to the next slide, and we will like show the comparison with the different cases later on. But the very interesting case as well here is that we had dual band antenna, right? So we have quite wide band that we want to analyze. So from like 500 megahertz, I would say, till like 400 megahertz, something like that. And this is something that I do, for example, in my work, I work with base station antennas, also quite wide band antennas that usually, and I do that as well. Like I split my simulation into two parts. So I simulate separately. It's the same model, right? But I simulate separately low band and simulate separately high band. So that is something that maybe very niche knowledge that maybe some people who only work with antennas, like kind of like these wideband antennas do. But this is something that you really need to do to not just have this kind of empty mesh that you don't need for example, low band. If you see the comparison of mesh elements for low band and high band, that's like a huge difference. And why would you want to run that for low band if you can just run like your appropriate mesh for low band? Or what do you think, Henrik?
No, exactly. Here, you divide the problem into two different parts because when you go to the high frequency part here for 4 gigahertz mesh, uh, we are gonna have a significant more amount of mesh elements, which gonna take longer time to simulate. Something else that you might be paying attention to here is that we have a scale next to each of these cars, and you can see that it's color coded. Uh, this is just actually a good checking point that we do before we start the simulation after we have done the meshing, and that is to evaluate the quality of the mesh. So all those scale means and the color coded means just a quality of the mesh. You want you're gonna so if you have a 1 here where you have the blue curves, that means you have a perfectly square mesh cell, and everything that is below 1 deviates from that perfect square. But don't get nervous here. This what we are seeing here is a perfectly fine mesh, and but it's a really good checking point to use that we have in Nullspace, that we can turn on this quality mesh.
Yeah, I
Um,
really liked it when I did like before my some simulation with the Nullspace, like with the electrical arch with the base station like tower, right? And when you actually can see that some points are problematic, some areas are problematic, and you see it in the color as well, which is kind of very straightforward, right? And then you see, okay, here maybe I need to see what I can do. Maybe I need to clean some surfaces or so, because as well a lot of like many antenna engineers know this struggle that you import the CAD, right? That is not appropriate, not good for electromagnetic simulations, and you need to clean it and you need to mesh it then. So that's very good to see like directly where you have these problematic areas.
yeah. One more thing I want to point out here is that if you take your eyes just below the two cars here, you can see that I've been adding some information about the mesh elements and memory consumption. So that memory consumption is how much RAM memory is getting consumed during the simulation process. So that means basically how big of a computer do you really need to simulate something like this. So on the low band, you can see that the memory is only consuming 8.5 gigabyte. And this is actually for the dense solver. So we are not doing kicking in this compression that you can see that I mentioned here on the right side. Because when we increase that and meshing this car at 4 gigahertz, so it's a mesh cell the mesh length is lambda over 5 at 4 gigahertz. You get much more mesh cells. And if you were going to run this with a dense solver, it will take 1 terabyte. But when we kick on our compression solver, which should not be confused with less accuracy, it's still a full base solver. It's fully accurate. It's just it's just doing it in a compression mode. And that only takes 56 gigabyte, which can be run on most typical antenna engineers maybe even laptop. I have a laptop here that this was ran on, and you can do it on yeah, any workstation that a typical engineer would use.
Yeah, that is great. And now we can move to results, right? With the metal roof results, and here you can see what I was talking about. So what we can see here is in blue we have our metal roof results. So antenna installed on the metal roof. So the antenna that we simulated the standalone, we just put it then on the metal roof, right? And run the simulation with the whole car included in the simulation with the full wave solver. And in the blue, you see with the metal roof, and in the green color, you see comparison with the standalone antenna, right? That we had before. And here, the first row is our low band, and then on the second row is our high band. So you can see that especially big difference is in the radiation pattern that I think many of you already expected, of course, because the car is massive, like piece of metal, right? So you can think about like what we saw before, this pretty kind of donut shape radiation pattern for 700 megahertz for PIFA antenna in the free space that like float in the air. But here we put it on a vehicle, and you can see that radiation pattern change. So that also like the signal distribution around your antenna also change. You cannot expect anymore that it will like behave the same as in your free space simulation. And we also see here that there is a bit of a shift in the resonance, maybe not as big, but there is some level shifted and some a bit of like resonance shift, several megahertz, something like that. And on the high band, again, big change in radiation pattern, and maybe not so much so big change in return loss in resonance, but that is kind of what we would expect. The like the metal car part, it affects mostly low band antenna, so we kind of will see the most effect on the low band antenna because of the wavelength, because the kind of car becomes the part of that radiation, right, of the low band. And Henrik, I don't know if you want to add here something, or we can move to the next.
Yeah, we can move to the next. We will talk a little bit about more about the difference between the
Yeah,
two
right.
cases in the last slide. So
Exactly. We will talk more about the final results when we have all our simulations with the glass roof as well. But here we have also interesting slide with the surface current of the antenna, and that's the antenna installed on the car. That's what I was talking, that antenna is now kind of working with the car. So kind of car is the part of the antenna. Henrik, what do you see here on this surface current presentation?
yes, so we see something really good. We see what we expect here. That we see that the surface current is really distributed across the whole car. We can see that it's mostly active on the top of the roof. But what we can also see here is that we have a good healthy simulation. And we also want to put this surface current plot in here just to illustrate that Nullspace can also do any type of plot that you expect from a 3D program. As you can see here is surface plot. We can also do near field plots and far field plots based on more of a vehicle with a plot around it. And surface currents is sometimes really useful to look at, especially when you have local resonances. You can zoom in and see really where the problem is, what is resonating here, and that is what I used to do it. This is a really helpful thing to be able to do.
Yeah, and also you kind of can see directly if, as you said, if it's like healthy, right? Like kind of like in in a
Mm.
bit of a medical term, like if it looks right, right? Like kind of
Yeah.
so if your simulation is actually like runs even correctly.
Yeah, and don't forget that the salespeople really like this type of plot. So so
It looks good.
it's always nice to put these out in a brochure or make it big for some type of marketing campaign. So it's always very nice.
Yeah, and so now we move towards the glass roof simulation. That was very interesting for me when we were kind of deciding what we want to do. We were thinking like, should we include glass roof simulation? And I really wanted to include that because for me it's very interesting. Like we want still the same connectivity in our modern cars, right? But we also want maybe a bit fancy cars, maybe want to have cars that look good with this glass roof and panoramic view. And so how does it work? Because glass is dielectric. And so it does not behave as a piece of metal as we had before with the glass roof, right? And also one thing that we need to here to consider is that glass, like this dielectric, has a thickness in the simulation as well. So Henrik, what approach here is the best?
Yes. So what we did here is that the car itself, it comes with uh, as a sheet metal body. That's what we use for the simulation because usually cars are stamped metal, thin sheets. So we isolated the roof part and we added a thickness here of 5 millimeter. We were talking with some experts in a car manufacturing to get these values here that you see. They could probably differ a little bit between cars, and we use a dielectric constant of 6.7 and then a dielectric loss of 0.01. And I just want to add a little more flavor here, Katarina, to why this can be important. Like my car I have here is I have a Honda Pilot. It comes in two different levels. One is with metal roof, and the other one actually has the most of the roof is glass.
Mm-hmm.
So even if you have the same car, they make it in the same in different
Right, different
configurations.
configurations. Yeah,
So
yeah.
and they most likely want to use the same antenna. So
Yeah, exactly. And I would kind of suspect that they want to use the same like shark fin antenna or something, and like inside's the same, like all the kind of maybe connectivity systems that you have inside are the same, but the environment is changed now, right? And so it was very interesting for me. Like you need to think about that. You need to design your antenna to work then in different, like in several environments kind of simultaneously. That's of course possible, but that is a challenge and that's something that you need to consider when you design this antenna. So, so here we have the interesting results, and what we see is the comparison between metal roof results that we saw before and glass roof. So the glass roof ones is in yellow and metal roof is in blue. First thing that really catches my eye is that we have a big resonance shift with the glass roof compared to metal roof uh, in our like matching, right? Matching of our antenna changes, and yeah. So if you use the same antenna, for example, in this case, if we use this antenna on our car, because it's the same car, we just changes roof, like in Henrik's case, right? It's just different roof material. So here it will not work already because the resonance shifted enough to kind of to have this problem with to some potential problem with matching, right? So you kind of need to think about that and maybe design antenna that has broader match in that area that you will like want to cover with different configuration, or like you need to kind of really simulate in different configuration and see what comes from that. And then again, if you remember before, we had first we had this beautiful omnidirectional donut shape with a single antenna. Then we had somewhat directive pattern that kind of radiated from the car, maybe what you would expect with some big metal sheet below antenna. And here we have something completely different with the glass roof, because it's dielectric, and it's also different dielectric that air that is like on antenna side, right? So radiation pattern is like doesn't kind of know what to do, and it radiates everywhere. And it also has a lot of different nulls that we really want to know about, because that nulls is where we will not get any signal. And for example, if we need to have signal in that direction, and then we have null there because of some kind of like configuration of our roof, we really want to know that. And then again, as I talked before, the most different here we see on the lower band, because that kind of car environment that affect a lot more on the lower band. On the high band, we don't see so many like differences. Of course, difference in radiation pattern, but for example, with the matching with resonance position, it's quite quite stable in this sense. And then if we go to the next slide, here we have the comparison of radiation patterns of all our cases. So you can see directly kind of how this progression is going. In the first case, we have our low frequency and high frequency for our standalone antenna, and it looks very nice. It looks as you would expect. Then we have somewhat directive radiation pattern of the antenna that's installed on a metal roof, and then we have very chaotic radiation pattern that is installed on a glass roof, because we have this dielectric there. So you can see here that I like this 3D kind of radiation pattern graphs, because maybe even for engineer it doesn't have a lot of information. We usually look at cuts, we usually look at like some other like patterns, right? Well, because we really need to know like exact kind of numbers, right? But here you see very visually that that change is it's significant. You cannot ignore it, right? You really need to simulate antenna in the environment. So if it's installed antenna, you need to simulate it in installed state, so with the car. If it's antenna that will be like inside, or is it like wearable antenna, or so you need to simulate it in that environment. If it's antenna that will be on a plane, you need to simulate it on a plane. So that's kind of the main point that I always try to show. And unfortunately, still a lot of people don't take it seriously. But I think that with this kind of good pictures that we show here, maybe more people will start getting it seriously, that it's actually like it changes a lot. And here, Henrik, if you can kind of show us what changes now. I talked about radiation pattern, but maybe you can talk about as well about the frequency shift.
Yes, so here what we are looking at is the three different cases for the low band. And in this example here that me and Katarina has shown today, we are using a PIF antenna. The PIF antenna has a pretty active chassis mode for the low band, which means that ground plane that is sitting below the PIF has a lot of currents. And the performance that we're looking at here is going to be pretty dependent on how much offset you have between the car roof and the PIF antenna. So in this example, we had about 10 millimeter offset. We got these results, but if that shifts a little bit up and down, that's also going to change how much frequency shift that you would get.
Yeah, exactly. So, and also, I would also kind of want to emphasize here one more time that it's okay to have this frequency shift if you kind of predict it, if you know that it's there, right? And you design in this in mind. But if it's surprise for you, if it's something that you only kind of discover in the prototype phase when you already have your antenna prototype, that is not good situation, because then you need to either kind of tune your antenna somehow manually, and sometimes it's possible if you have some like matching network or some, but sometimes it's not possible because you don't have any maybe tuning possibilities there. So you kind of maybe go in another prototype round because of that. And then you implement that knowledge. But if you think about that in the beginning, then you kind of maybe skip one or two prototype rounds that you that's not necessary. And then the last thing, kind of like on this antenna simulation that we wanted to show is that with this approach, with the Nullspace like simulation approach, we can simulate as much like a lot of amount, big amount of ports. Sorry, I started to talk weirdly. We can simulate several like ports or like a lot of different ports in the same simulation, in the same run. And for example, here what we did is that we installed antenna 2.4 gigahertz Wi-Fi or Bluetooth antenna inside the car, and we checked if there is any coupling between our antenna that we simulated before, and we showed you results before, and that antenna, because that is very like real case. We have in our modern cars a lot of connectivity, right? We have like Wi-Fi, Bluetooth, all these things inside the car. Then we have some like radio, we have cellular, a lot of things. And if you think about they kind of work quite closely on like some frequencies that can be close together. And even if the frequency is not the same, for example, like here we have 700 megahertz, we have 3300 megahertz, 3600 megahertz, and then Wi-Fi is 2400, right? It's not the same frequency, but sometimes in our antennas we have some parasitic resonances, we have some like radiation peaks that we don't expect, and they can happen on that frequencies that we kind of maybe even didn't think about, but then there is some big coupling happening. So that is very, very good to consider as well. So here we simulated coupling between our antennas, and so you can see it's very, very low. It's like virtually non-existent, and that is very good. But it's something that you really need to control as well.
Yeah, yeah. Highlight again here that exactly what Katarina said, that here we had 3 ports, but maybe in a typical system here, if we had, for example, an 8x8 MIMO, a few Wi-Fi antennas, you throw them all on the car at the same time, it will not increase the simulation time, because we are doing the full wave solver, the full fidelity. Number of port does not increase any simulation time, which is a very big benefit, or and also something to really think about when you think about those asymptotic solvers, that where you probably have to simulate one by one port, and then the time adds up, plus it's not as accurate. So
Yeah, right.
just want to highlight that again. Okay, should we move on? Yeah, I already started the talking a little bit about just pointing out a few things about traditional simulation limitations. We have the sequential port analysis at scale. That is also true, for example, if you run HFSS frequency domain solver, which will probably not even be practical for those cases we have shown here today. But if you did that, they will turn on that iterative solver that will also be port by port simulation. We have volumetric meshing required both for time domain solver in CST and frequency domain solver, but here we are using method of moments. We are only simulating the surface. So if the volume really increases, but the surface area is still about the same, it will not increase your simulation time. You don't need that bounding box that you need in other solvers. You just need to make sure that you follow the recommendations in your mesh settings on the surface, and then you're ready to go. That is, let's move to the next slide and highlights a few things here with what Nullspace is doing differently. So we do the surface mesh only. We have the higher order geometry. What that means is that we are not just doing um, two-dimensional surface or mesh elements. We are actually having three-dimensional surface elements by using quad 9 elements if needed. And that is really convenient for high curvature elements. And then we took advantage of this, and this comes really handy in for really big simulation, the compression algorithm. That is Nullspace secret sauce. That's how we really can compress big problems into 96-97% compared to that full dense solver. And we have the higher order basis functions that also increases the accuracy and let us have a little more coarser mesh cells. I'm gonna move on just to one little more thing here that I want to mention that we just came out here at Nullspace, and that is our this is a little different from what we just show you with the vehicle, but we wanted to just highlight the AI powered CAD cleanup that you can do, and here it's demonstrated using a CubeSat. So as RF engineers, when we import vehicles that we're gonna use in our simulations, a lot of times they are not prepped for an RF simulation. So to improve meshing and minimize the simulation time, we want to do a cleanup. And in Nullspace, we have this AI automatic cleanup that can go in and detect certain features. As you can see here up to the right here, we are identifying small surfaces, holes. We have the radiuses that we also identify. And on the right side, we basically just deleted all this using this AI cleanup tool, and that significantly simplifies the mesh. It gives you the same exact results, but it significantly reduces the simulation time required. So this is a really helpful feature that any RF engineer can do directly by themselves in the Nullspace prep software. And with that, I am gonna hand it back over to Masha for a finalizing slide here before we move into our Q&A.
Great. Thank you, Henrik and Katerina. So this is our last slide, and yes, we'll go ahead and move into Q&A. So keep those questions coming. We see a lot of them in the chat and the Q&A window, so we'll try to address as many as we can. The ones we can't address, we'll follow up with an email after. And if you can be concise when asking questions, it's hard to read long questions and then respond as well during the webinar. But we will address the ones that we don't address today in a follow-up email. But just looking into the future and kind of what some of you working specifically in an automotive industry could maybe take away from this webinar regarding Nullspace. So Nullspace is really positioned to remove the solver as a bottleneck, right? As mentioned, this is our modern answer to electromagnetic full fidelity simulation. So if you need to run large-scale electromagnetic simulations at full fidelity, that's computationally out of reach. I saw there's a question somewhere, somebody asked, how would you run the simulation at ANSYS? And I believe, I'll let Katerina and Henrik answer. I believe the answer is you really can't, because it's just too large of a problem. So Nullspace's aim is really to remove the solver as the bottleneck in your simulation process. And then, as mentioned, Nullspace, underlying Nullspace is a very powerful Python API. It's more flexible and powerful than, let's say, if you've played around with the Python API at ANSYS. Nullspace's API is much more open and more powerful to set up complex optimizations. And because Python is a language of AI, and in today's world, and if some of you are playing with AI in your design and simulation, during your design and simulation, Nullspace is really designed to be driven by AI if needed. And just you can fine tune and play around with all kinds of settings and with all kinds of complex optimization setups when you're working with a Python API. And again, if you're concerned about ADAS, which many of you on this webinar I know are, if you need to validate your antenna systems, 5G, V2X communications, and radars, etc., coexist without interference. Before you actually build the vehicle, Nullspace can help you there. Again, because these are electrically large problems to simulate. Or if you need to ensure that your platform meets evolving ADAS requirements by identifying electromagnetic conflicts at the design stage, again, that's where Nullspace can help. And then the other thing I wanted to point out, so Nullspace was founded by myself and my other two co-founders. We all have PhDs in engineering. We've used simulation tools, not just on the electromagnetic side, but for many years. And we have been tortured by complex and expensive licensing of the legacy tools. And so Nullspace's licenses are simple. So there's no token pools, there's no, seed fights, or all of our licenses are floating licenses. And there's no paying for add-ons. So once you pay for your annual lease for your license, you get all the future releases if you need them that come up, and you get the use of all of the CPUs and GPUs you have available on your machine as well for that one annual lease pricing. And if anybody we see some questions about pricing, so if anybody's interested in that, I'll let you know how to reach out to our sales team to ask those details questions. And with that, I'll hand it off to Katerina and Henrik for the Q&A session.
Yeah, we will start Q&A. We have a lot of questions. One thing is that slides will be and recording will be available, right, for all the participants. And will be sent later. I think I see a lot of good questions, and really happy about that. Really like good questions on the webinars. One question that I found is in the classroom case, radiation and return loss very disturbed. Can we use this antenna still, or do we need to tune the antenna? Exactly, that is the point of that. I wouldn't. Personally, looking at the results that we see that we shown today, I wouldn't use this antenna on the glass roof case, for example, because we have significant shift in radiation in matching, and we have a very big difference in radiation pattern, and we have a lot of nulls there that kind of look quite unpredictable. So we don't know where they will end up. So for this case, I wouldn't use this antenna particularly. What I would do if I was like in this kind of like case that I really needed to design this antenna, I would go back to single antenna simulation, and keeping in mind what I had with my glass roof simulation, I would adjust the antenna, maybe make it broader in bandwidth, right, for especially on a lower frequency. And then I would have this tolerance, right, to cover this frequency shift when I have different configurations. And that's how I would do it. Henrik, do you see any good questions?
Sorry, Henrik, in the Q&A, just I don't know if you've seen that there's a couple of questions about meshing in Nullspace versus other tools, and then the dielectrics.
Yes, I saw a few about the mesh, and there was question about you can do local meshing in CST, so what is the difference? The big difference is that in Nullspace, as a user, you will always control your mesh. So that's the default setting. You will always be in control of your mesh. So that is as we try to explain during the webinar, a good thing, because maybe it seems to be a little difficult in the beginning, but when we have very straightforward guidelines, and as you start playing with that, you will learn a lot more about your antenna, where to put the denser mesh, and you will always be in full control. And you always try it out on a smaller model before you if you're going to do a phased array. Before you go to the full array, you always can test your mesh on one element, but then you have confidence that it's going to be the right mesh for that element. But again, we have straightforward guidelines on how to do that. And as you start using Nullspace and get trained, you're going to get all those guidelines, and it's going to be pretty straightforward.
Henrik, I saw one question about the simulation time. Do you remember what time did it take for For single antenna, it was very fast, of course, but for like the metal roof, for example.
Yes, usually we don't put that in the presentation just because it's gonna depend on the
Yeah,
computer
right, of
system that
course.
you have yourself. But for my system, I was running those metal roof antennas um,
Yeah,
on my laptop. So it took, I think, 1 hour for the low band case, and it was overnight. I forget exactly, but something like 10, 12 hours for the metal roof case for the high band
for high frequency.
for
Yes.
high frequency. But also because we are using the high or the fast frequency setting here, that means that we're just setting a start and stop frequency. The software will take over and decide how many frequency point that is needed. If you were running this car over and over again, you would probably take a little bit different approach and effective that a little bit more. You might remove the dipole antenna that we included here just to minimize the frequency points that needs to be run to get the full response. So that is still a little thing you can play with to make it even more faster and efficient. But that was about what it took, about 8-10 hours for the high band case.
Yeah, but it also like you need to keep in mind that this is the full wave, and for me, it's really like fascinated that also could run this low. Like I have very very bad laptop, my personal laptop, and I could run this low band with a full car. On my laptop and yeah, in the full wave. For me it's like some miracle or something. Another question that I saw here is about so if we replaced our antenna with a phased array, can we use our car as somehow like beam shaping, beam forming detail that we can kind of like use and scan our antenna in like different direction? um, well, I guess theoretically you can do that. Like if we just think about a theory of antenna ratio, so you can have some beam shaping properties if you use your ground planes in some like shapes, right? Or you have like particular angles or so. That is possible. But I have hard time seeing it in the car, especially because in the car we care a lot about visuals, right? How car like looks like. And also I guess some aerodynamics also important, but I don't know what is more important, the visual or like some aerodynamic properties. So I don't know how would you do that in in the car, because just with some flat roof I wouldn't even think that you can do any beam like shaping kind of with a flat roof in the car. You need some like kind of like special shapes. And also but you can maybe think about other direction, maybe not particularly car, but maybe to do something with the radome. There are some radomes that can be like used in the utilized in this like beam shaping, beam forming, like some maybe radomes that include some layers of like lenses, like act as lenses, or have some like layer of meta surfaces there and something. So I think that is more realistic in this case, that use actually the car itself.
Thank you,
Henrik,
Katarina.
do you see anything interesting?
Yes, I was.
I
Um,
saw one also interesting question about like maybe short one about if the car is ground plane, act as a ground plane or as a secondary radiator, and the car is a ground plane. We don't connect the antenna to the car. It's very important to know the actually to short antenna to have this like short circuit where antenna is actually connected to the car. uh, you need to have some like what Henrik explained before. You need to have some like a kind of capacitive connection there, not galvanic metal connection with them, right? So
yes.
you see here on this like current that the car is it's a part of antenna, but it does not act as a like radiator itself. Because if you remember our S parameters result, we have standalone antenna with dual resonance, and we have the same resonance. They are still in place with the metal roof and with the glass roof. They just maybe shifted a bit, like different matching and so, but the antenna works with the same resonance that it was like it worked before when it was standalone antenna.
Thanks, Katerina. One quick question about dielectrics. We can quickly answer. Is null space suitable for simulations of antennas with dielectrics?
Yes, of course, no problem. Yeah, in this example today, we had the radome that was covering the shark fin. Even in the standalone case, even we had removed that just for the picture, so you can actually see the PFA, but the radome was there in all the simulations that we shown.
Yeah, glass fiber. Yeah.
Yeah, glass fiber radome, and then also for the glass roof, of course, that's a dielectric layer. And so yes, there is no problem to simulate any type of dielectric materials in null space. You can also add dielectric properties over frequency that change over frequencies. You can use any type of dispersive model like the Debye model. We support that. We support anything that you would expect in terms of material properties and defining those material properties and using those dielectric materials in the simulation.
Henrik, yeah, interesting question about the mesh. So for high frequencies specifically, because we saw how mesh changes between frequencies, well, how to get the accurate values? What is the rule for that?
Yes, so in this simulation, we were simulating with the second order basis functions. That means that we can have a little coarser mesh. So for those, we have a guidelines of lambda over 5. So we just basically, when we are when we are doing the meshing, we just request that on this car surface, we want a lambda over 5 mesh size, and then we just mesh it with that size. So that's all the 2 lines that you tell the code, and that's what happens. So that is our standard recommendations, and that is always what I use and always what works. If you were
Yeah,
gonna use first order basis functions, then you use lambda over 10
right. Yeah.
mesh size.
But that's what we did in our simulation, right? We had the
Yep,
lambda over 5, lambda over 10. Yeah.
yep.
And the last question, I think, what we can take for today, it's maybe for benchmarks. I think that, Masha, you have a lot of good benchmark with the different software tools that maybe people somehow can access.
Yeah. Yeah, thank you for asking. I saw that question about, oh, do you compare it to actual
Yeah.
experimental results? And I think it's important to remind everyone, and I didn't do this in the beginning. So Nullspace is not an academic tool. It's not something that just we came out with. It was actually under development for over a decade in stealth and a defense contractor. So my co-founders actually founded a defense contract company that was focused on designing, developing, and manufacturing very sophisticated RF devices for the Department of War here in the US. And so they developed Nullspace as a tool because they had access to ANSYS, CST, FICO, a whole bunch of government full fidelity tools for radar and antenna design. And they just felt like those tools were outdated for what they needed to do. And so that's how Nullspace was born as a solver. And so then it was sort of grown and developed in stealth in a defense contractor for over 10 years while it was being used on actual production of DoD quality defense systems. And so it's been validated many, many times over. It's again not something that just came out recently. The reason why perhaps you have not heard of Nullspace and why we're so new is because the company itself is new. So we're about 3 years old as a company, but the solvers themselves have been developed and validated for many years. So we do have a whole bunch of benchmarks, and we're happy to walk folks through them. If you have any questions about that or would like to talk about scheduling a demo or a trial of the software or interested in purchasing Nullspace, please reach out to info@nullspaceinc.com. I'm going to put it in the chat as well. And yeah.
I think that was everything that we could take this time, but we will update some questions there are a lot of very interesting questions, and we will maybe follow up with the after the webinar on some questions
Yeah,
of that. So
yeah, for sure. Well, thank you so much. Thank you everyone for being here, and stay tuned for more exciting webinars from Nullspace. Thank you, Katerina and Henrik.
thank
Thank
you
you,
very much.
everybody.
Bye bye.
Bye-bye.
Bye bye.